Hello, we're UASB. We're Upflow Anaerobic Sludge Blanket Reactor, and we're here to present to you about what we've done this semester. I'm Emily Liu.
Hi, I'm Emily Wood.
Hi, I'm Had Ishfaq.
Hi, I'm Dominic Grasso.
Hi, I'm Kara Smith.
Hi, I'm Francesca Bard.
I'm Lydia Lagorga.
I'm Shania Fang.
Hi, I'm Valentine Starnes.
Hi, I'm Kira Frederick.
And hi, I'm Katrina Chen. Wastewater is any water that has been used by humans domestically, commercially, industrially, or agriculturally. So this is going to include households, schools, farms, factories, or urban runoff. And wastewater includes a variety of different pollutants, such as nutrients like nitrogen or phosphorus, toxins, heavy metals, pathogenic bacteria, or biodegradable organics. And over 80% of Earth's wastewater is released back into the world without treatment, and untreated wastewater is a problem because it can cause extensive environmental damage, such as pollution. So when there's a high concentration of water pollutants and organic matter, it's going to be able to kill marine birds, crustaceans, seaweed, or even other aquatic animals. Also, wastewater has nutrients that can cause eutrophication, and this causes algae blooms, and the algae is going to deplete the water of oxygen, especially in the lower layers. So it's going to make it really hard for animals like fish to survive. And also, wastewater can contaminate a community's drinking water, and this is going to increase the spread of waterborne diseases such as cholera and others seen in Figure 3.
So why are we doing wastewater treatment at AguaClara when we've traditionally done drinking water treatment? Well, we think the answer is simple. It's in alignment with AguaClara's vision. As Katrina said, there's an inherent need for these communities to start getting wastewater treatment. AguaClara is in the business of envisioning a safer, cleaner future for both people and our environment. After our successes with drinking water treatment, our Honduran partners encouraged us to start seeking solutions for wastewater. Now, how have we approached this problem? We have tackled this challenge in the same way that AguaClara tackles all of its problems. Our reactor uses metrics of success, such as limiting electricity usage, cost, trying to make it easily adjustable, using easily accessible materials, and by emphasizing these parameters, we enable AguaClara and UASB to support these communities in the most sustainable and best way possible. Now for the go beyond part. At AguaClara, we not only try to fix the problem, we want to do it well, and if possible, go beyond to extract additional benefits from our system. Our design for a UASB leverages biogas capture, which can offset electricity needs inside the communities for things such as cooking and heating. This project has been a long time coming. It was founded in 2013, and wastewater subteams have been working ever since on wastewater designs. This semester, we have begun our first pilot plant at the Ithaca Area Wastewater Treatment Facility, and is helping us push our progress towards our vision.
So the current wastewater system in the U.S. has conventional treatment plants that have very, very high costs and use a lot of energy. So usually the wastewater will go through preliminary, primary, secondary, and tertiary treatment that will rid of organic pollutants that are bad for the environment. So generally this has very large land requirements and requires aeration, which is very costly. So AguaClara was looking into smaller, more modular designs that we could implement in smaller communities. So a UASB stands for an Upflow Anaerobic Sludge Blanket Reactor. So the way this works is wastewater will flow upwards through a sludge blanket of microorganisms that will degrade pollutants like nitrogen, phosphorus, and organic pollutants. And then through this process, methane is produced, which can be used as a biogas fuel locally. And then the effluent wastewater will have lower levels of nitrogen, phosphorus, as I was saying before. So this has a lot of benefits for small communities just because it is much smaller, easier to implement. It has a lower cost as it doesn't need to use aeration. It also doesn't use any energy, which is great. And then again, biogas product can be used as fuel. So this is what AguaClara was looking into smaller communities.
So the purpose of the UASB team is to expand AguaClara's reach from clean drinking treatment to wastewater treatment. So the difference between our UASB versus a conventional UASB is that ours is low cost, customizable, electricity free, and locally sourced. We're essentially using the same principles we've been applying to our clean drinking water technologies to improve our current wastewater technologies.
Here's a CADed model of our reactor. I'm going to tell you how water flows through it and how the treatment process happens. So if you follow the red arrows, the water is coming in through a tipping bucket in the top. We currently have our system set up so that the bucket tips every 15 minutes and gives a pulse of wastewater to our reactor. When the bucket tips, the water flows down through the pipe on the outside and to the bottom of the reactor. This is a really important design because we want to eliminate preferential flow. Preferential flow in our reactor limits the growth of microorganisms, which are important for the treatment process. So by making sure that the water hits the bottom and evenly comes up through the sludge blanket, we eliminate preferential flow. After the water comes in through the bottom, the level in the digester rises, and the clean water, which is at the top of the reactor, can flow out and through our effluent line. We added a sampling port to our effluent line this semester because it made sampling much simpler. A few other new design elements are on the side. We have sludge ports because the second and third reactors that we have made are not translucent, so we need to be able to gauge how fast and how high our sludge blanket is growing. Some other really cool features, we have our fog weir at the top. This will allow us to take out the layer of fats, oils, and grease that will accumulate in our reactor after it's been running and treating wastewater for a significant amount of time. And then the ones right below it is to control the sludge blanket level so it doesn't get too high. At the top, we also have a biogas tube. We're not currently producing biogas, but when we do, that tube will connect to a bag, which we'll be collecting. And then, as Val said, that can be used as fuel for communities using this product.
In order to compare our effluent against conventional designs, we ran tests at the Ithaca Area Wastewater Treatment Facility using the same standard procedures that they do. So we test for biological oxygen demand, BOD, chemical oxygen demand, COD, phosphorus, and fecal coliforms BACT. BOD and COD are the most common ways to determine the composition of wastewater because they measure organic pollution. So what they do is they measure the dissolved oxygen that microorganisms need to decompose the organic matter in that water sample. BOD uses microbial digestion of oxygen to measure organic matter, whereas COD uses chemical oxidation reactions. So higher values of dissolved oxygen indicate more polluted water, whereas lower values indicate less polluted water. So after our startup period, we expect to see a large decrease in the COD and BOD values when comparing our influent to our effluent. UASBs are known to have high removal rates of BOD and COD, so we're making sure our UASB is up to par with this by testing for this once a week, whereas we're testing for phosphorus and BACT once a month. As of now, we ran through our tests and we're running through phosphorus in a few days.
So kind of to give a summary of some of the test results, we have sent several early mornings in the lab. So the first one, which you see in figure 13, is our fecal coliform test. So the little modules in the test, they're bright yellow, which means there is a lot of bacteria and pathogens in our effluent water. If it had low to no levels of bacteria, you would be seeing like a pale yellow to a clear test. But this is not super unusual. UASBs are not known for their high bacteria or pathogen removal, so we are not too concerned about that, and this is not our main test we're focused on. Like Franny said, we're mostly focused on the COD and BOD test. Results from that, as you can see in figure 12, which is our effluent water, which is obviously a little cleaner than what traditional wastewater looks like coming in. So our water quality is about halfway between the influent water that's coming, the influent wastewater that's coming into the plant, and the plant's primary. So that is their water after they have treated it through a primary treatment. So this is good because it means we are actually, the UASB is actually doing something, we're treating it, but it does mean that it's not quite up to the level where we want it to be yet. We want to get results that are close to the plant's primary. So our goal is kind of like to wait and see what happens, to keep testing it every week, like Franny said, and hopefully that it will improve over time. It should, because the sludge is still in the startup phase, which means it still has some growing to do. But we will see.
So during our literature review period, we had three main principal goals that we were focusing on. The first was to determine which factors can characterize or better decrease the startup time associated with our reactors. The second was to determine which parameters we need to record better in order to better gauge the efficiency of our reactors. And our third goal was in order to determine if our design system is still optimal for the conditions that will be faced when implemented in Honduras, and if there are any modifications we need to make. In regards to startup time, the literature suggested that there were three principal avenues we could go down to help try and decrease our startup time. The first of these was metal cation addition. So this is very similar to the process that AguaClara uses during its water treatment of adding polyaluminated chloride ions to help increase flock size, but we would be adding iron and calcium instead. The second suggested technique was to add organic, inorganic hybrid polymers into our reactors during the startup time. So this helps with initial granulation processes because it will help boost the structural integrity of the sludge blanket within and preserve its integrity as variable flow rates are coming through and may lead to washout of methanogens. The third technique that was suggested by the literature was nitrogen and phosphorus addition, and this is basically just going to help stimulate the growth of the microbiome within the reactor. So in respect to our second goal, which parameters we need to record and which tests we need to perform in order to better gauge the efficiency of our reactors, again, there were three principal avenues which we decided to go down. The first was taking the temperature of the effluent that's coming out of the reactor, and this is because the microbiomes within these reactors are incredibly sensitive to changes. So this means any change in temperature or any consistent temperatures which lay outside of the optimal temperature zone of the microbiota can really mess up our efficiency. So in order to test these temperatures, we can determine where the efficiency lies. Additionally, temperature also increases the solubility of methane within the reactor, and this can kind of alter the kinetics and make methane production thermodynamically unfavorable. Secondly, we decided to start testing our pH levels because this can help determine if there's any variability or shock that is experienced by the reactor or sustained by the reactor during organic loading rates that are incredibly high. So this is because if you look at the diagram, you can see kind of the flow of organic matter through the different microorganism groups within our reactor. And when there's a high organic loading rate, acetogens will produce much more because they have a bacterial yield that is 5 times greater than methanogens. And so this means that a lot of organic matter will make it less favorable thermodynamically to go through methanogenesis and instead result in an accumulation of volatile fatty acids, which increases the pH. So testing this helps us to determine if there is a shock event. And then finally, we want to look at tracer testing, which is basically to better determine if there are any preferential pathways that have flowed, as Lydia was showing in our diagram how we've tried to mitigate that. And then finally, we were also looking at design changes. So because we are working in rural, small Honduras communities, it's important that we try and mitigate the shock loading that can occur, the changes in organic loading rate. And this is because in a small community, it's very dependent on individual uses and it's very stochastic, the amount of organic matter that's coming through. So we were thinking of using a holding tank to try and kind of average out or mitigate the extremes of high and low periods of organic concentration in our influent. We also looked at a recycling stream, which would help distribute the organic loading again. So some of our effluent would go back into the influent in order to keep the organic loading rate at a more average concentration. However, we have to be careful with this because if our velocity is too great and exceeds more than 1 meter per hour through the reactor, we could experience washout. And then finally, we looked into different types of granules. In the article that Katrina was looking at, we see the difference between multi-layer granules and then more diffuse granules. And currently we're operating with multi-layered granules as seen in the top of this diagram. However, we could also explore different types of granules and granule formations to help optimize our efficiencies. And I'll pass off to Ahad.
All right, so I'm going to be talking about modifications and challenges that we encountered with the second reactor. So as Lydia mentioned before, the second reactor is a continuous flow reactor and it is opaque. Now, while this is cost efficient, this does pose the problem of us being unable to see inside the reactor. And that's bad because we can't follow the sludge blanket and we can't determine whether the microbial community has properly established itself within the reactor. Now, to get around this problem, we decided to drill holes in the side of the reactor. And after multiple trials or multiple runs of trial and error, we decided that a 0.5-inch diameter was the right size. So what we did was we drilled holes along the length of the reactor, a foot apart, and we attached valves to them. And now, once we open the valves, we can determine the density, the quality, and the height of the sludge blanket inside. Another issue that we faced with the continuous flow reactor was the fact that the effluent was really hard to access because you had to uninstall it because it was leading into the drain line. And the way we got around that was we decided to use two valves and a Y. And the way this would work is we'd have one of the valves would continue down into the drain line as the original design, but the other valve would be used to test the effluent. So all we have to do now is we have to, we close the valve leading into the drain line, which forces the effluent up and around the Y into the other valve, which we can then simply open and test the effluent demand. And here's Shania.
So this semester we started fabricating the third reactor. As of now, we finished building the holding tank, the frame of the holding tank. We drilled in the necessary holes and glued in the steps in the main body of the reactor, and we finished cutting the sludge, FOG, and influent pipe. What we have left to do is to build the effluent part and to piece everything together. We still do not know whether or not we want this third reactor to be continuous flow or pulsated flow. We're currently waiting to see the results from the first and second reactor. However, because of the first reactor, the microbial community within the sludge is still not stable, so we can't tell if the pulsated flow is efficient or not. And for the second reactor, because of design modifications that have been done over the past semester, we still have not begun testing for that.
As Lydia mentioned earlier, we'll be storing biogas in this big 60-liter container. It's like a little bag, well, a big bag that you see in the rightmost picture on the slide. And we've been measuring the volume using a wet test meter, which is the picture on the left. Unfortunately, this semester, we haven't really seen a lot of biogas accumulation. Our biogas bag has been pretty flat. And so we came up with 3 hypotheses for why this might be. The first is that there could be a hole in our biogas bag. Secondly, somewhere else in our reactor, there could be a gas leak. Or third, because we're in the startup period, it's totally possible that we're just not producing much biogas at all. And it's really important that we figure out what is happening with the biogas because it's our most straightforward and easiest measure of success of our reactor. Because if we're producing biogas, that means that our organisms are working and digesting organic waste. So we've confirmed that there is not a leak in the gas bag itself. We did this just by filling it up and inflating it and then putting it under pressure, and there was no leakage there. So future work for the next semester will be to determine if our other 2 hypotheses are correct. We can see if there's a leak somewhere else in the reactor by pumping a known amount of air or possibly nitrogen into the reactor and seeing how the wet test meter and the gas bag respond. We can also do a soap test where we cover connections between pipes with a layer of soap, soap or soapy water, and see if any bubbles form. And this leads into other future work that we need to do the next semester.
Cool. So I guess for future works for next semester, there are 4 things that we want to address. The first is the second reactor. So we want to because we didn't finish it yet this semester, we need to first re-water test it to make sure all the glue is like working and there are no other holes that will cause water to leak out of the reactor. And then we also need a gas test, the second reactor, to make sure that there's no biogas leaking because we want to collect that. And then we also need to put any additional plumbing, such as like the influent, to connect that to another part for the influent. Okay, and then also the effluent, draining out any sort of excess effluent that we have, so that we can put that back into the Ithaca area wastewater treatment facilities wastewater. So then for the third reactor, we want to finish fabrication. This includes things such as sludge ports and the holding tank frame and the holding tank cover. We have yet to finish that. And then third is testing. So as Emily previously said and Dominic kind of touched on, we are going to establish a testing schedule so that we can do that regularly, as well as add temperature testings and pH testings. And then finally, for lit review, we need to do additional lit review to see what kinds of influent we'll be receiving if we're trying to implement this in Honduras. Yeah, so thank you for listening to our presentation. Hope you enjoyed it. It was a long one, but yeah.